Hi there. So this video is going to be about calculating the scattering phase shifts. We have phase shifts for each value of L, which is related again to the angular momentum of the electron or the particle that's scattering off of the target atom or molecule. And in this case, again, we're dealing with only a spherical interaction. So kind of those L values are independent of one another. They don't mix. You can calculate the phase shift for each value of L separately, and then kind of add them together in a way to get the final result, total cross-section, things like that. But what I want to talk about today is how are those phase shifts related to the scattering amplitude, and then we know from the last video how that scattering amplitude is related to the cross-section. So often this is called partial wave analysis. We are always talking about an expansion in terms of spherical harmonics or functions that depend on L. So just to remind you, right, in the past we had done an expansion of the wave function psi in terms of L and M, and we used spherical harmonics, YLM here. It turns out that, for a spherical interaction, there's no dependence on the angle phi, which means that M equals 0. And so we can actually expand in other functions, which are related to the spherical harmonics, called Legendre polynomials. They depend on the cosine of theta. Now, I could write everything in terms of expansions in spherical harmonics, but I want to write these down here because you'll often see them, for example, in the textbook by Griffiths or other textbooks. They're just another way of writing the angular part of the wave function. The other thing I've put here, just to make things simpler at the end, things kind of cancel out a bit, is I've changed from UL over R to UL over KR. Now K again is that square root of 2ME over h bar squared, right? It's kind of the wave number. It depends on the energy. Now the reason I can do this, it doesn't matter when you plug this into the Schrodinger equation, the K and the R cancel out, you get the same equation for the radial functions. So they satisfy the same equation. But the point is, I expanded the wave function in terms of angular functions, right? And we can talk more about expansions and functions later on. But the point is, I'm going to do this same thing, expand the other functions that are important, right? And kind of skipping ahead a little bit. If you remember in the last video, we talked about that the wave function goes asymptotically as sort of an incoming wave along the z-axis, a plane wave, and then it goes out as a scattered spherical wave, e to the ik over r, and the coefficient that multiplies that scattered spherical wave is called the scattering amplitude, f of theta. So our plan here is to make an expansion in terms of our angular functions, Legendre polynomials in this case, of each of these two terms in the asymptotic function, so e to the ikz. I'm going to try to save a little bit of time by not going through all the mathematics, but the mathematics here leads to this expansion coefficient. So the coefficient multiplying our angular function for this case turns out to be I to the L times 2L plus 1 times JL. Now JL is the spherical Bessel function that we've talked about a little bit in the past. It's related to the Riccati-Bessel functions. If you go back to those videos, but basically it's a function that depends on L that's related to the sine of KR. Now, if I want to expand e to the ikr over r, well, e to the ikr over r is a radial function. It only depends on r. So I just have to expand f of theta as a constant f of L times the angular function PL cosine theta. And so I get this. Now, just again, to make things simpler, I'm going to consider in detail only the L equals 0 case, only the L equals 0 term or the S wave. It's often referred to the S wave or S partial wave. Now you can go through all the details for the other waves, or in general, you get a similar result. But again, I don't want to dwell on the detailed algebra and mathematics. I want to get to the main point if I can, while at the same time going through a bit of the mathematics. When you deal with the L equals 0 term, in this asymptotic form, it turns out for L equals 0, P0, your Legendre polynomial, is 1, right? And it turns out psi of r and theta goes as just J0, right? L is equal to 0, plus e to the I k r over r times F0, only our 0 part, or L equals 0 part of the scattering amplitude. We can also recall, maybe from a previous video, that asymptotically our spherical Bessel function goes as sine of kr minus L pi over 2 over kr. Now, again, I'm just looking at L equals 0, so it just goes as sine of kr over kr. Using a little bit more stuff that we did in the previous video, using the Euler formula, sine of theta is equal to e to the I theta minus e to the minus I theta over 2, I can rewrite this asymptotic form here as this. So I'm just plugging in stuff, right, and rearranging. Psi of r theta as r goes to infinity is this minus 1 over ikr e to the minus ikr over 2i. And then I get an e to the ikr over r function, multiplying f0 plus 1 over 2ik. So again, just to reiterate what I did there, I used this to write my sine of kr, and then I plugged it in here. Right, so I wrote my J0 of kr using this formula, but with this expression for the sine, and then I rearrange things a little bit. So I'm skipping a fair amount of algebra there, but hopefully you get the main idea. I'm just trying to write asymptotically in terms of e to the minus ikr and e to the ikr, this wave function psi, what it should look like, the incoming and outgoing scattered wave. Okay, now I kind of made a little error here. Recall also that, that asymptotically we can write our radial functions in terms of a phase shift. Now UL, right, for general value of L, you'd have a minus L pi over 2 here, but including only the S L equals 0 wave, we get A times sine of kr plus delta 0. But then we got this 1 over kr term here. I guess what I should say is this is not U0, but this is U0 over kr, right? I'm writing that whole radial part of my expansion of the function in terms of this phase shift. So the plan here, I want to now analyze asymptotically how this goes in terms of our phase shift that we wrote when we wrote our radial functions, and compare it to our asymptotic form that we have here and here, which is written in terms of the scattering amplitude. I'm going to compare those two forms, and I should be able to figure out what the scattering amplitude is in terms of the phase shift. Okay, so I'm comparing these two things. I got to do a little bit more manipulation here, though. I need to again use my Euler formula again, right? That e to the I theta, sine of theta equals e to the I theta minus e to the negative I theta over 2i, but I'm going to use I delta. If I use Euler's formula to rewrite the sine function here, I get this. You get a over 2i, so maybe I won't say it all out, but you see I have just changed the sign into an e to the I kr and I delta 0, and an e to the I kr minus I delta 0. And I get this a to the a over 2i kr in front here. Okay, now let us compare this equation 9 to our equation 7 that we had written down from the scattering amplitude form of the asymptotic wave function, right? So I didn't hold my paper quite right there, but let's do that again here. But hopefully you can see, right? I'm comparing. I'm comparing my previous form, which came from the form, asymptotic form that had the scattering amplitude, with my form that comes from the phase shift and the radial function. Right, so we kind of have two asymptotic forms we're comparing. Now you can see that A, right here, this I have a negative e to the minus ikr over 2I. Well, A has to equal e to the positive I delta 0 to cancel out this term and make these two terms equal. So I find that A is equal to e to the I delta 0 if I want to make those two things equal. Also, this other term here, F0 plus 2ik, has to be related to this, right? It's the ikr part. So I see that F0 plus 1 over 2ik has to equal A, which is e to the I delta 0, times over 2ik times I to the delta 0. So I just am comparing the two parts of those functions. And then I can solve for F0, and I find this. It's 1 over 2ik times e to the 2I delta 0 minus 1. Okay? Now, recall, I've got my S wave scattering amplitude. Well, this differential cross-section for that S wave part, right, only for L equals 0, is the square of the scattering amplitude. Now by square, I mean you take the complex conjugate times the function itself. Complex conjugate just is taking all the i's, you know, making them negative, and then multiplying by the original F0. Doing a little bit of algebra, you can get down to that it's 1 over 2k squared sine squared delta 0. It's a constant. It doesn't depend on theta. It's what we call isotropic. This happens at very low energies that the S wave, L equals 0, is the biggest contributor to the cross section. And for very, very low velocities, very low energies, you often get a constant cross section. Okay, we can talk more about that. But again, I just want to show the relation. The other thing you can get is the total cross section. And if you integrate, well, first of all, let me show you in general, right? For the general case, for all values of L, you have to add up all the L values that you got for all the different components, Legendre components, and you get this expression. So you find that generally FL is 2L plus 1 over 2ik, e to the 2I delta, or delta L minus 1. And these are the coefficients in that expansion of PL of cosine theta. So I can get the scattering amplitude as an expansion in terms of those functions. Now we got a, you know, if I want to get the actual f of theta, I have to plug in what those functions are. But I just wanted to show the relation. Now I could integrate f squared, and I would get my total cross section, which turns out to be 4 pi over k squared, sum over L times 2L plus 1 sine squared of delta L. So you can see that there's sort of a partial cross section here. Maybe I should write it down. But the partial cross section is just 4 pi over k squared times 2L plus 1 sine squared delta L. That's for each value of L, there's a partial cross section they add together to get the total cross section. So a lot of times people analyze scattering results in terms of L equals 0, 1, 2, or S, P, or D phase shifts, or S, P, or D cross sections. But the total actually that you compare to experiment, you got to add all those partial cross sections together. Okay, I think hopefully that's not too confusing. But I think maybe that the next video I can do is to try and describe the scattering code and what it's actually doing. If we can run it, the cool thing is that you can calculate this and actually compare it to experiment, and it gives good results for a lot of cases. The other piece that we need is the scattering potential, which I'm just going to give you probably for now, but we can start to talk about those potentials. This stuff is all described in one of the chapters in Griffith's book or other textbooks. But again, it goes into more detail on the mathematics and stuff. Hopefully from this, you at least got the main idea. Last thing, recall how we get the phase shifts. We solve for the use of L close to the target out to a value of R that's far enough away that we can match it to the asymptotic form and get the phase shifts from that matching. Once we have the phase shifts, we can use these formulas to calculate the cross sections in the spherically symmetric case. Okay, I think I'm going to stop there, and hopefully I haven't overwhelmed you at this point.